Hello and welcome to this Pell 5-minute short on calculating a required relief rate for a pool fire case. So this is part of a series of 5-minute shorts just around relief device sizing, and I've picked the fire case because it's nice and simple to do and it follows on quite a series of sheets. So we want to calculate how much heat's going to come into our vessel and then how much energy we are going to absorb and then how much vapor we're going to release or need to release through our relief device. So where I'm looking now is I've got required relief rate, and I'm going to use one of these fire equations. Now there's 4 there, which might be a little bit confusing, and this is all to do with different standards and different ways of doing it. So the sheet I've used is the API 521 method, which is probably the most common method most people use. And if you're following API, that's for pressure vessels effectively above 1 bar gauge design pressure. API 2000 for low pressure storage tanks, so anything below 1 bar gauge effectively, then API suggests use the API 2000 method. That fire gas is for a gas-filled vessel, so if you haven't got any liquid in there, it will estimate a relief rate. Basically, it's a gas expansion case, but do worry about how hot the vessel's getting and how fast it will fail. That's a different issue, but just a quick warning on that. And then the Picher-Gate is the old ICI way of doing, the Epicher-Gate way of doing this. And it basically what that does is where API disagreed with itself, and they are different, the 2005-21 methods. Basically, ICI looks at it, well, we'll create a hybrid version that is basically the worst case of both, because then hopefully it can't be wrong. So depending which standard you want to use, depends which version you want to use. We're going to stick with the API 521 method for this particular case. Now you can see I've got, again, the yellow boxes. I need to fill these in, and I need to start putting molecular weights, relief valve set pressures, etc., etc., etc. in this. I could go into FizzPack and I could open it up and I could generate some data. So I could say I want toluene or methanol, whatever it might be, at its boiling point, and just filter that straight through or copy it across. There's a much better way of doing this in Capri. So if I go to this fizz props table here. So the way I found this, again, you go physical properties, this button here, fizz props, and then we'll do this again. So I'm going to press this button here, speed of light, it will open up. There we go. Right, so I'm just clear the workbook. I'm going to add a new component. So we're going to go for methanol. We can take the extended search off. We can find, there we've got methanol. And what we're trying to do, because we're in a fire case, we've got bubble point from pressure. And I could do an isothermal, I could define temperatures and pressures, whatever it might be. But we're going to stick with bubble point from pressure on this one. And then I know that I'm relieving at 6.6 bar gauge. So the way we got that, I typed in 6.6 bar gauge, bar there, bar absolute, but it's okay because it understands units. So that's going to convert 7.6 bar absolute. I can press calculate. It's going to go and contact FizzPack or the engine behind it. In truth, you get a little bit of a twirl, and it's going to fill in this sheet now. So we've got our methanol, we've got some data up here, we've got our temperature and pressure, and then we've got our stream, vapor, and liquid variables that we're going to use and need. So really quite neat and simple way of getting fizz pops in, and I'll show you why it's so beautiful and so much better to do it that way than the other way in a moment. So regardless of my fire case, so I'm going to say my fluid. Well, actually, my fluid, I can go back here. I'm going to say it's methanol. I've got a molecular weight. So let's do that one. Molecular weight of 32. So my valve set pressure is 6. My design pressure is 6. I'm going to have 10% overpressure because it's a PD 5500 vessel. My relieving temperature is in there, and my latent heat of vaporization will be down here somewhere. There we go, latent heat of vaporization. So that gives me some data. Start doing the calculation. I need to think about my fire case. So do I have adequate drainage? So I'm going to say yes, it does. And I'm going to say I've got passive fire protection. And I'm going to say no to other environmental factors. I need to have a wetted surface area. So in a previous 5-minute short, we did a wetted surface area calculation, and it's that value there. So I've got 16.3 square meters. This is if you want to add an allowance for pipe work, you want to do something, I want an extra 10%, whatever it might be. That's entirely optional. There's nothing in the standard saying you have to do one thing or another. It's annoyingly quite quiet on that kind of subject. We're just going to stick with the area of the vessel at this point. Now we've got passive fire protection. Now if you had a proper thermal conductivity, you could put that in. I'm just going to put some numbers in here because personally, the way we do pressure relief, we don't go below 0.3 for that environmental factor. So I can always just put any number in here to drive this low and then just say, yes, I want it to be 0.3, which is what that has done. Any other environmental factors you want to put in there? Say normally the drainage we've specified the fire protection. They're normally the two you would worry about. It's given me a heat input. It's applied my environmental factors, so I've got my 0.3 in there. I can see my heat input is 128 kilowatts, and I've got so many kilograms an hour. And then that's converted it into normal meters cubed an hour there. So if you are doing API 2000 type calculations, you need to convert this back into normal meters cubed an hour there, because annoyingly low pressure storage tank relief devices are all done in normal meters cubed an hour there. That will give you a conversion for that. So that's an answer. That's given us so many kilograms an hour. Now, for those who've done the course, we know we've got methanol and toluene. We've got a 50-50 mix in here as well. But what we're going to do is we're going to put, we're going to change it because toluene's our defining case. And this is the beauty of linking these things properly. So we're back to the fizz props. I can go back up to here. And I'm going to clear the workbook this time. I'm going to add a new component and I'm going to put toluene in. I don't need extended search. There we go. It's added it. Still the same pressure, 6.6 bar gauge. We're still doing double point. So let's calculate. So that's going to twirl away and it's going to repopulate this sheet. But because I've linked things, we'll double check I've done it properly, then any change in this will go straight through into this calculation. So you can see we've got our molecular weights changed, toluene, we've got our pressures, we've got our temperature, we've got our new latent heat. So that is just filtered all the way through. And that's the real power of Excel and linking things correctly. So, and we've all done calculations. You change something, which part of the calculation does this change? If we use the links and make sure we're taking like one source of truth, one value, and link that through, if we change that value, then it filters through. We reduce an awful lot of time trying to find that mistake. It makes it a lot easier for checkers to check, approvers to approve. But that is fundamentally it. So we've now got some heat being absorbed into our vessel. We can then think about what we're going to do next to the size of valve. Thank you very much.